Sounds good. You ready?
It's recording.
Okay, I was talking to him. So 3.7b is homework will be same page, same stuff, just different concept. So 3.7 part 2. Once upon a time, this was apparently it would have to be a lesson that I gave. I needed a sub to be in here for me, and I wrote up these like super detailed notes of how to do this lesson. I must have just left this behind for students to do without me in the days before video. So if you're watching this video, anybody, and it's not the year 2021 and you're somewhere in the future, a key item to have is probably the PDF of the notes, because instead of writing it on the board, I'm just going to sort of read through this page. So today's about a thing called differentials. So differentials are in existence to estimate an amount that something changed, not a rate of change. Okay? Derivatives measure rates most commonly. And when derivatives measure rates, they do that perfectly and instantly, instantaneous rates, that kind of stuff. Differentials are an imperfect way to estimate not a rate of change, but an amount that something changed. I'll further illuminate that when we go on up a second. So here's our strategy. We're going to do the derivative on both sides of an equal sign, the sum equation that we have. And at some point, there's going to be a bunch of variables in it, okay? And if at some point you do the derivative of A, we're just going to write down dA. Kind of like when we did the implicit differentiation lesson, every time you did a y derivative, you just left the y prime. Okay, so every time you do a derivative of an A thing, leave a dA. If the formula has r's in it, leave a dr. If the formula has a v in it, leave a dv, and so on and so forth. Every derivative piece, you'll do it like you usually expect to do it, but then you're going to leave a d whatever next to it. Same idea as the y prime, just a little different punctuation. So, for example, these first couple, a equals pi r squared. That's a fairly famous formula. That's the formula for area of a circle. If we turn that into what's called a differential equation by doing the derivative of the a would be a 1. I don't really want to write the 1, but I am going to write a dA because I did a derivative of an a. If I do the derivative of pi r squared, I'd get 2 pi r. And since that was based on r's, I leave a dr. Second one down, v equals 4/3 pi r cubed. That's volume of a sphere. So if I do the derivative of the v, that's a 1. I don't want to write the 1s. I just write a dv. The 4/3 pi r cubed derivative, the 3 would cancel the other 3 when I do the derivative. So that's 4 pi r squared, and leave a dr. That last one for circumference of a circle, the c becomes a dc. The 2 pi r just becomes a 2 pi, because 2 and pi are just numbers. So when you do the derivative and the variable vanishes, you just leave the numbers. So 2 pi, and I leave a dr. And again, what those d's mean, the dA is how much the a changed. The dr is how much the r changed. It's not perfect, but it's a pretty quick way to estimate how much something changed. If the radius changes a little bit, it's going to cause the area to change a little bit. If the radius changed a lot, it'll cause the area to change a lot. So we're measuring how much that changed. So like if the area was 3 and the area became 3.2, the dr, the change in radius, would be like 0.2, the amount of change by. Does that make sense?
Yeah.
So that's the concept. We're just trying to estimate how much stuff is changing. And if you have an equation, if one thing changes, the other stuff has to change likewise. Then I do some book examples. So on page 181, there's an example 6. So page 181, example 6. The first thing you have to do is read the thing to decide, like, what formula do I need? So it's saying, like, radius of a circle, blah, 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 area. Okay, so we either need to be given, which we are in the paragraph, or you'd have to look up area of a circle equation. So a equals pi r squared is the equation. And sometimes they'll give them to you. Sometimes you're going to have to look them up somewhere and remind yourself, what is this? Or sometimes it might even be a wordish story where you have to write your own equation. Maybe it's a squared plus b squared equals c squared, Pythagorean theorem, or who knows. You might have to do a write it yourself kind of moment. The first step is have a formula. Second step is do the derivative, and I'm not going to talk through that. That's one of the three we just did up above a second ago to create dA equals 2 pi r dr. And then you'd have to read the story and just plug in. So when they say radius had an initial value RO of 10, wherever you have an R, which we had one left standing, I just plugged in a 10 for R. Then it says that it changed by dr of 0.1. So where I have the dr, I plugged in a 0.1. And then it asks us to calculate dA. So to calculate dA, that's the only variable that's been left standing. Everything else got a number plugged in. Just multiply everything together and we're 2 pi. Good on that. I skipped the part of that example where it said compare dA with the true change delta A. We'll look at the homework and see if they did that. Since I didn't even do it in the notes, it probably doesn't affect the homework. But if we wanted to do this by like a true change, what you'd have to do is take the original 10 and plug it into pi r squared. That would be 100 pi. Then take 10.1, because if the radius was 10 and it changed by 0.1, it's now 10.1. You could take 10.1 and plug it into the original equation. 10.1 squared times pi, that in the book by doing peeksies, they say that's 102.01 pi. And then to figure out the change, you'd subtract the 102.01 pi and 100 pi and get 2.01 pi. So in our story, our estimated derivative-based way, we got 2 pi. The true real answer by doing more plug-in activity and actually subtracting stuff is 2.01 pi. And in a lot of settings, like 0.01, who cares? Like, we missed it, but close enough. It would sort of be the attitude on
You have
that.
to do that.
What's that?
We ever have to do it.
They might do that. If they say compute the true change in the homework, then you're not using calculus, you're using some kind of like an algebra 1-ish kind of plug in and do some subtracts. You good on that? So then there's an example 8. Example 8 says Earth, suppose the Earth is a perfect sphere, which it isn't, and you determine the radius to be 3959, give or take a 0.1 miles. They ask what effect that give or take 0.1 would have on an estimate of surface area. So the first thing to plot a formula, you'd have to fixate on surface area and spheres. You probably don't know the area formula, surface area formula for spheres. It might have been in our notes from like chapter 1 when we did algebra stuff, but I don't think so. It might be inside the front covers of your book somewhere where people have written some geometry formulas historically, but it might not be. But in 2021, Google is your friend. Ask Siri, what's the formula for surface area of a sphere? By the time we take the test, I do think some of those are expected to be known in your mind. So if you do have things that you look up, you might want to start to create your own little, I had to look this up cheat sheet to study off of later, so you don't just take for granted what happens. There's nothing ever on a test that isn't on a homework. So if you had to look it up on the homework, you might want to just take note of that somewhere. But for surface area sphere, it's S equals 4 pi r squared. If I go to do the derivatives there to create what's called a differential equation, we go dx equals 8 pi r dr. And then we skim the question again to look for numbers to plug in. The 3959 was the radius. So that's going to plug in for the r. The give or take 0.1, that's the change in the radius. That's how much they might have mismeasured the radius by. That's the dr. So the 0.1 would plug in for dr. And then you math that up, and the only thing we lacked is the ds, and it ends up being 9,950-ish. If you multiply in the pi, it's not exactly that, but it's close to that. Does that make sense? Mm-hmm. So then they talked a little bit about things that were mildly interesting. So just to reinforce the theme, again, this isn't like perfect, okay, but what they're saying is here, if you had mismeasured the radius of the Earth by a 0.1, you would mismeasure the surface area by 9,950 square miles. which they say is roughly the size of the state of Maryland, which might seem like a big deal. I'm sure it's a big deal to people in Maryland, but really, who cares about the people in Maryland, because they have that hideous flag, so they really shouldn't really be listened to on much of anything. If that's their flag, I mean, they just lose all sort of say in anything. I mean, if you can't even create a flag for your state, how are you expected to be taken seriously? 9,950 miles, they say, is roughly the state of Maryland. I'm going to go viral now on the state of Maryland or something.
Severe hatred for their flag.
I'm going to get hate mail from the state of Maryland if they love their flag.
I'll be canceled.
Yeah, that's rough. It's a rough. I think that's a rough flag. Anyway, but 9,950 square miles, roughly the state of Maryland. That seems like kind of a big deal. But if you look at a globe, a full globe, and try to find Maryland on it, like the whole surface area of an entire globe, Maryland is like a dot. You know, so the .1 making 9,950 miles didn't actually do much to the mistake of the globe. It's like 0.005% off by mismeasuring the radius of a tenth of a mile. Semi-interesting conversation, I guess, even though 9,950 square miles is a lot of square miles. Not in that context of an entire globe. Let's see. Next thing I had, there was an example 9. So example 9 says, how accurately, okay, this goes in reverse, okay, so example 8, you knew how much you missed the radius by, maybe, and you were trying to be curious what that does to the, like, final answer accuracy. This one, we have an idea of the final answer's accuracy, but they're trying to trace back to how much could we miss the radius by. So example 9, they're saying, how accurately do we need to measure the radius if we're trying to measure the surface area and we want to be within 1% of being correct. So we're willing to be off a little bit on the surface area, we're willing to miss it by a full percent. How accurate do we need to be on the radius to do that? So like before, pick an equation. They gave you the equation. If you didn't have it, you'd have to Google surface area, spheres, find it. S equals 4 pi r squared. While you have the formula, you might as well instantly do the derivative because it's the derivative chapter. So you're always going to have to do the derivative. You might as well do it immediately and then figure out what to do with it. But ds would equal 8 pi r dr. And then I did this a little bit how I like to do my Algebra 1 stories. Like when you first take Algebra 1, you do a lot of questions like a number is increased by 3 and the result is 10. And you kind of just patiently go through the sentence and replace each word with a symbol. You know, the product of 5 and a number decreased by 4 is 11. Go at that. I just kind of took that approach here to this number 9. I just took their sentence and did some replacements. So their sentence boiled down to surface area within 1% of a true value. So I'll work back from right to left. The true value of the surface area was 4 pi r squared. The true value of the surface area is given by the original surface area formula. Okay. Working to the left of that, the word of means to multiply. 1% is better to be used as a percentage or fraction usually than a percent. In our setting, going fraction will be the optimal way to do our homework. Within is a word that can just do a less than sign. And then before that, we're trying to do an assessment of how much did we miss the surface area by. And how much we missed the surface area by, that's not the original equation. We already used the original equation. That must be where the derivative has to go. So it has to go somewhere. Does that make sense? Mm-hmm. And then our question at hand is, how much could we have missed the surface area by? Okay, how much we missed the surface area by, that's the dr. The dr is the change in the surface area. So I set about trying to get the dr alone. I've got 8 pi r dr. I want the dr alone. So I'm going to have to divide by an 8. If I divide by the 8, that'll turn the 4 into a half. I have to divide by the pi if I'm trying to get dr alone, and that just cancels the other pi. If I divide by the r, that's going to cancel away one of the r's in the r squared. And if the dr is alone, it would be less than, still the 1 over 100, 4 became a half, and there'd be a single r left standing. You with that? The algebra, getting the dr alone, you want me to rewind? I worked from, I got 8 pi r dr less than, and I want the dr alone. So I divided by the 8, made the 4 be a half. Divided by the pi, so pi vanished. Divide by the r, which turns the r squared into a singular r. Okay? And then I'm going to just translate back to English. Okay? And like we've always done historically in those algebra word problems, if they come in with a story, we translate that to math, do math. But then we usually try to translate it back into an English thing again. So I just matched the way I came in. Less than means within. The 1 over 100 makes us still be percentages. It's a half of a percentage now. I threw the word of in because it's multiplying, and then threw the word radius in because r was left standing. So to just say this in English, if we miss the radius within half of a percent, our miss on the surface area would be within 1%. And that's what we were trying to figure out. You know, how accurate do we need to be on the radius to have that 1% accuracy on the surface area? The answer is we can only miss the radius by a half of a percent. We better be pretty good at measuring the radius. Does that make sense? Then I'm going straight to the homework page. So 185, 185 we're working from 25 to 43. And I'm going to do 25 free of charge because it's a little different than any of the book examples. So I just always do that first problem as an example. So 185, the directions for this first little group of homework that goes from 25 to 30 says there's a part A that they want you to figure out delta F. Delta is always an algebra 1 symbol. There's no calculus to do the part A of these questions. Okay, the delta question is an algebra question. We sort of talked through that when we did the first example, example 6, and it asked us to find the true change, and I hadn't done that on the notes paper, and we just kind of talked through how we would do the true change, and you said, would we have to do that on the homework? And I said, I don't know, maybe we'll see. The answer is yes, that's what the part A's are. So here's a sample of that. So for 25, they're telling you, they give you a function, a formula, x squared plus 2x. They're telling you the original x is 0. They're telling you the dx, which means the change in x, is 0.1. What I like to immediately do is then figure out a final x by adding those together. If the original x was 0 and the change in x is 0.1, adding the original with the change will always give you the final x. So that was my first line of notes here that I did just to set me off was I did an x with a subscript of f for final x would equal a 0.1. And the math on that was artificially easy because one of the numbers was 0, but like on number 28, the final x would be 1.1. On number 29, the final x would be 0.6. So if we add those together, we can figure out the final x. Does that make sense? Okay. So then part A, what we would need to do to figure out how much of a change there was in the total formula is always plug in the final x. After you do that, plug in the original x. That gets you 2 different results. And to figure out how much of a change that caused, we're going to subtract the results that we got. So for this part A, for number 25, I would take my final x of 0.1, I'd plug it into the original formula, the x squared plus 2x formula, 0.1 squared plus 2 times 0.1, math, that should get me a 0.21. Then I'll plug in the original x, which is artificially easy on this question. So we're plugging in 0, we get out 0, but usually there's a little more to plugging in the original x. If we get a 0.21 and we get a 0, we're always going to subtract, and subtraction's picky about order. Always do the finals result minus the originals result, otherwise your sign will be wrong. So we'll do the 0.21 from the final minus the 0 from the original, 0.21, part A, mission accomplished, we're good. Okay. Then part B, they say find the value of the estimate df. Okay, and I think we talked about this before. It's not a coincidence that delta and d are used. Delta starts with d. D represents delta. Both the d and the delta are representatives of change. Just if I say delta x, I'm talking about an algebra 1 kind of change, a subtraction-based change. If I'm talking about dx, I'm talking about a derivative-based calculus measurement change. But these both represent changes. That they didn't pull these symbols out of thin air. They deliberately chose some of this stuff. So B, it's derivative time. So the original formula was f equals x squared plus 2x. So I did the derivative of f, I put a df. The derivative of x squared plus 2x will be a 2x plus 2. And for the first time when we did the derivative, there was a multitude of things there, adding and subtracting. Multitude is a strong word, but more than one thing, adding and subtracting. So I wrapped that up in parentheses as a group, and then put a dx. Because the dx technically would go with everything you did an x derivative of. And I'd rather not write dx, 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 dx if I have lots of x's I did derivatives of. It's simpler to just wrap it up and then just put a dx that goes with the whole family, if that makes sense. And then I plugged in. Okay, if we're plugging into 2x plus 2 dx, the x gets replaced with the 0 that they had given us in the beginning of the story. The original x of 0 gets plugged in there. They had told us a dx of 0.1, so we plug that in. Plug, 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 do a little math, and that gives us a 0.2 for the dx question.
How come it's not 2x dx plus 2 dx?
It could be. You could write it as 2x dx plus 2 dx. I just didn't feel like writing dx a couple times. Because if I gave you a question like this, I'd rather write 4x cubed plus 15x squared plus 12x plus 7 in parentheses with a single dx than to write 4x cubed dx plus 15x squared dx plus 12x dx plus 7 dx. Does that make sense? Mm-hmm. They're both correct. I just like to say writing. You good on B?
Can you go through like that again?
So the original formula had f equals x squared plus 2x. So if I do the derivative of f, I'm just writing df. When I do the derivative of x squared, it was 2x. The derivative of 2x was a 2. And then I could have either written dx on each piece. I just chose to throw it in parentheses and put a single dx, so I didn't feel like writing dx twice. Okay. Then we're plugging in. So the original x of 0 that they typed us in the book, the 0 gets plugged in for x. So 2 times 0 in my parentheses plus 2. And then the dx they had typed us in the book was a 0.1, so we just plugged that in for dx of 0.1, math it out, and that was 0.2. That makes sense?
Yeah.
Those two answers should usually be pretty comparable, if not identical. Probably not identical, but could be. They could be identical. Okay, but they should be pretty close. And then C is just an easy one. C, they want the approximation error. They just want you to subtract the two answers we just did. 0.21 was true answer. 0.2 was a guesstimated answer. So how much did we miss it by? Subtract those, and you can subtract those in any order. It doesn't matter. Okay, we do want always a positive result, no negative results. So just subtract it in whichever way gives you a positive result. And it's 0.01. Those are generally super close to 0. There's usually not much of anything left there for the errors. If you get an error that's like 50, that's probably not it. Unless it was like a globe question, like that one. The error on the one was like 9,950. You know, that's a lot, but not for a globe. Any question with percentages? Other than the within questions, I think we skipped any parts of the homework that have percentages to them. Let's do a quick homework walkthrough. You good with stuff so far?
Yeah.
Okay. So 25 sets you up for 25 to 30. It's basically the same steps. So 31 is easier. 31 is like where we came in. The very first couple notes, back on the page 1 of the notes, where I have the arrow drawn, where we very first started to do derivatives of the formulas, that's all you're doing on the group that starts with 31. You just have to take the V equals equation, do the derivatives to get a dV equals equation. And I already actually did that one for you. I already did number 31 when I did the notes, because it was the second one of that 3 that we came in on. It's already there. You continue doing that as far as 36. So 31 to 36, they're giving you the formulas on a platter. You just have to create the differential version of those formulas. That seem okay with there?
Yeah.
That's also a good place to, if you need formulas, there most of them are. That'll be a good bit of what we're doing. 36 for a while, then up to 43. They're all a little different. Some of them are kind of like the examples we already did. Some of them kind of stand alone. 37 looks a lot like that very first one I did about circles kind of stuff. The ones in the middle look more like the second example probably I did. The one where I went word problem translation, there's 2 of those. 42 and 43 look like the word problem translation question, like that example 9. One thing that catches my eye and my memory as I look at this, a couple of the questions play radius versus diameter games with you. So you just have to be ready once in a while to cut something in half or double something to make there be a consistency in the problem. Because all of the formulas are radius based. So when they start dropping you diameter information, just cut any diameter information in half to have radius information. But that's something to be on board about. Give it a go, I guess. That's all I've got.